In this video, we will be discussing Hooke's law and how to approach solving Hooke's law physics problems. So when studying springs and elasticity, Hooke's law was developed by the 17th century physicist Robert Hooke. And Robert Hooke noticed that there was a stress versus strain curve for any material and that it had a linear region, so that within certain limits, the force required to stretch an elastic object such as a metal spring is directly proportional to the extension of the spring. And so this was written out as Hooke's law. And so here, looking at the springs, we can see a regular spring right here, and that when an object is suspended from the spring, it's going to pull down towards the earth due to the force of gravity. And the spring will stretch, and it will stretch until it restores the force of the spring equal to the force of gravity. And so that if we added two objects of equal weights, then we're going to see that the spring stretches twice as far. So that what we see is the amount of stretch is proportional to the force pulling on the spring. And this means we can use this amount of stretch to measure the size of force using a spring balance. So that when we look at Hooke's law, we can see Hooke's law written in this form right here. F equals K times E. Now the F stands for the applied force, and this will be in units of newtons. The K is the gradient, and it's in units of Newton meters. Now this is going to be unique to each form of spring used. And then the E is the extension of the spring, and this will be in meters. So what Hooke's law is stating is that the force needed to extend or compress a spring by some distance known as x is proportional to the distance. We have a typical Hooke's law problem, and the problem says if a spring has a spring constant of 0.5 Newton meters and it is stretched 0.5 meters, what is the force of the spring? So we go to our formula that our force would equal our spring constant, which would be in Newton meters, times the distance that the spring stretches. And so to solve this problem, we would take our 0.5 Newton meters. We would multiply that times the distance that the spring stretched, and so we would have an answer of 0.25 newtons. And a lot of Hooke's law's problems are that simple. Now sometimes we are asked to determine how much a spring will stretch. And to do so, we can use Young's modulus. Now this is also known as the elastic modulus, and it was developed by a 19th century British scientist by the name of Thomas Young, and it's a measure of the stiffness of a solid material. In other words, it's the mechanical property of linear elastic solid materials, and so we can define this as a relationship between the stress, which is the force per unit area, and the strain, which is the proportion of deformation of an object. So let's see how we would use Young's module to determine how much a spring would stretch. So before we begin our example problem, I want to point out this chart, and you're going to see that the chart has different substances, and each one has its own unique Young's modulus measurement. Those are in units of Newton meters squared. And so we're going to take these standards, and so when we look at Hooke's law and we look at our stress over strain, Young's modulus is going to be appearing in this lower area of strain where we look at our proportional deformation. And so we're going to apply this. The example we're going to use in our problem is going to be steel. And so you're going to see that we're going to use 20 times 10 to the 10th, and this is a standard. We'll use this in our upcoming problem for our solution. Now here we have our problem. Suppose that the steel A string of a piano is 43 centimeters long and has a cross-section area of 6.5 times 10 to the 7th. How much will the string stretch when a force of 710 newtons is applied to it by a piano tuner to bring it up to pitch? Now before we continue, what we're going to do is we're going to take these 43 centimeters and we're going to need to convert that over to meters. And so when I show you the solution, this is going to be changed over into meters. So to solve the problem, E is Young's modulus. We have our stress divided by strain. F is going to be the force exerted on the object under the tension. In this case, it's going to be 710 newtons. A is going to stand for the actual cross-section, and so in this case, it's going to be 6.5 times 10 to the negative 7. Our triangle L is the amount by which the length of the object is changed. In this case, this comes back to this being steel, and it's from our previous slide, and it's 20 times 10 to the 10th. And L sub O is the original length of the object. In this case, it is 4.3 times 10 to the negative 1 meters. Remember, we changed the 43 centimeters to meters. So we're going to take this information, we're going to plug this into our formula, and when we solve our answer, we will get 2.35 times 10 to the negative 3 meters. Now here we have one additional Hooke's law problem to solve. We have a patient's leg was put into traction, stretching the femur from a length of 0.46 meters to 0.461 meters. The femur has a diameter of 3.05 centimeters with the knowledge that the bone has a Young's module of, now let's look at this right along here. This is supposed to say 1.6 times 10 to the 10th power. It was a little difficult to get that typed in correctly. But it was in tension, and what force would be used to stretch the femur. So let's use this right here, this information, plug it into our formula, and see if we can solve the problem. So as we begin the solution of our problem, remember that we will be using this equation where E is the Young's modulus, F is going to be the force exerted on the object under tension, A is going to be the actual cross-section area, the triangle L is the amount by which the length of the object has changed, the L sub O is going to be the original length of the object. Now as we go through this problem, what we know is that F is our unknown, and so we're going to rework this equation, and so we will use it in this form to solve for F. Our problem stated Young's modulus as being 1.6 times 10 to the 10th in pascals. We were given our original length of our spring as being 0.46 meters. To get the amount of change in the stretch of the spring, we have to take the 0.461 meters minus the 0.46, which was the original length, and so we get a change in length of 0.001 meters. Now area is not given, but we were given the diameter, and so in order to get the area, we're going to use the formula pi radius squared. And so if you remember, the radius is half of the diameter, and so we have pi times the radius squared, and we're going to get 7.30 centimeters squared. We need to convert that over into meters squared, and so that's why we have it as 0.073 meters squared. Now that we have this information, we will plug it into our formula. We have that plugged in right across here. So we have our y, our triangle L divided by L sub O, all of that times our area, and so we will get our force in newtons.